So we give these days in the beginning of the year. So chapter 9, lecture 15. Today is August 3rd. So this is the most excited, better part of the class. The most important part, which is applications. We learned about single state. Single state can be steam table or ideal gas. Even we learn about process from one state to another. And we took some application like first of thermodynamics, closed and open systems. And we also talk about the second law of thermodynamics. Hello, can you hear me guys well?
Yeah, we can still hear you.
Okay, great. So what happened? Today we're gonna talk about cycles, about Otto cycle, diesel cycle, Brayton cycle, Rankine cycle. There are a lot of cycles in our class we're gonna cover. Let's see the first one, which is the gas power cycle. This chapter is gas power cycle. What is gas power cycle? It's here. So here we're gonna set a lot of processes makes a cycle. We're gonna discuss cycles. We're gonna discuss cycles. We started with Carnot cycle. We have a lot of experience with Carnot, which is the most ideal efficient cycle. So 9.1, 9.2, we're about Carnot cycle. For example, if you plot the PV diagram, we plot TS diagram. We started here, 1, 2, oh, here, 1, 2, 3, 4, 1, 1, 2, here, 1, 1, 2, 3, 4. Constant temperature, isentropic, temperature, isentropic, adiabatic, and reversible. Everything is reversible. So this is constant temperature, adiabatic, constant temperature, adiabatic. This is the PV diagram. This is the TS diagram. This part is the work net. This part is the heat net, which is Q and W. The area under the TS diagram is Q. The area under the PV diagram is W, per unit mass. This is also per unit mass if this is a specific property. This is semi-recurrent cycle. The most important thing, we know 1 minus Q low over Q high. For example, this is power, like for example, heat engine. If the heat engine, heat thermal 1 minus Q low over Q low, this is always correct. It's equal 1 minus T low over T high if it's Carnot. This is only if Carnot. Maximum efficiency, ideal. And this is the efficiency. There is something called COP, very similar, but for refrigerator and heat pump. So this is 9.1. 9.3, we're going to talk about the assumptions. Air, standard, assumptions. All our cycles, in reality, they are open. So in the car, you have the piston cylinder. It's open. It's open system. This is like a cylinder. It's open a valve, close the valve. So the air go in or the fuel go in, and the exhaust go out. This is exhaust stream. Sometimes in the cycle, this open, this is closed, this is closed, this is open. Sometimes both are closed. So the system reality is open, but we assume it's closed. So this is called assumptions. We assume it's closed, but it's not. In reality, it's not. It's supposed to be open. But we can assume it's closed, which is in the real most important part, it's open. So we can hear the air stream and the fuel stream comes inside. The air is much larger than the fuel. We can assume mostly air, like it goes to 20 to 1, ratio 20 to 1, 12 to 1, sorry. So 20 to 1, 15 to 1. So it means too much air compared to fuel. We assume completely air, which is wrong. but good assumption. So generally, for the fuel, for all fuel and air cycles, first we have one, let me draw it here. 1, 2, 3. We have like 4 stages. Actually, 4 stages here, guys. The first one, they are enter the engine. The fuel and the air enter the engine. So when we have combustion chamber, like boiler, then we have the power. This is the important part. That's what my output is, the power stroke. Then we have exhaust. All the exhaust going out. Then repeat, air and fuel going in, combustion, power, exhaust. Air and fuel going in, combustion, power, exhaust. This is the cycle for all air standard assumptions. This is a typical cycle. What are our assumptions here? Let's write the assumption together. There are 4 assumptions. In 9.3, section 9.3, we have 4 assumptions. 4 basic assumptions. 1, we assume closed system. In reality, it is not closed. Filled with air. Filled with air. With air. This is page 2. Actually, I did not post a lecture, but I'm going to post it soon. Maybe today or tomorrow. So closed system filled with air. It's filled with air and fuel. But we assume mostly air. It's actually open, but we assume completely closed, as we will see in our problems. Okay, guys? Is it clear for you? So this is closed system, which is open. It's filled with air, which is not correct. It has both. But we have huge amount of air compared to fuel. All processes are reversible or internally reversible. So we assume all are reversible. The most ideal. This is 2, this is 3. They are all reversible. Reversible is a process that you can reverse without having effect on the surrounding. So this is the most ideal process. The combustion, which is hard to treat, very hard, we're gonna assume is replaced by heat addition at constant volume. We're gonna assume that the combustion is heat addition at constant volume. So if it's air, if you're talking about Q, so it's look like CV delta T. It's closed system, and we're adding heat. So CV delta T. So this is usually typically what we're gonna do. The last assumptions, the exhaust. Exhaust is heat rejection. Maybe constant volume, maybe constant pressure process. So in reality, this exhaust, it's open system and something going out, something going in to replace it. But we're gonna say no, just heat rejection. Then we're gonna continue the cycle. So it's a cycle. Part of it is heat rejection, which is assume Q low, something we reject some heat. And that's it. We continue the cycle, which is not cycle. Actually, we input new fluid and we burn them and let this fluid, the gases go away and enter new ones. But no, this is hard to treat now. So for simplicity, I assume just heat rejection. Just we dump some heat outside, which is Q low. Any questions? Any question, guys? In these assumptions, We assume closed system. All processes are reversible. Combustion is heat addition at constant volume. Exhaust is heat rejection process. Heat addition and heat rejection, like Q high and Q low, to be similar to what we have done before. Okay, guys? 9.4, what I got? ICE, internal combustion engines. ICE, 9.4. It's ICE, internal combustion engine. ICE. Remember the police, ICE police for immigrants? Remember that. So internal combustion engine, ICE. We have two types of internal combustion engines. We have two types. Something called spark, like our car. Ignition. We create the ignition by spark. Or compression. Ignition. Ignition. So as you know, we have triangle of the fire. We need to have fuel. We need to have air, oxidizer. We need to have ignition. This is the triangle of create fire. You just have fuel and air, no problem. If you have air and fuel, or ignition and fuel, there is no, you cannot have any fire. But in order to have fire, you need to have the three together in the same time. So we have the ignition. So usually we have this and this. We need to know how the ignition look like. The ignition can be spark, like spark plug in the car. We have in a car something called a spark plug. I don't know. Do you know this or not? Something like this. This is a coil. It creates here sparks. It makes the ignition every cycle. So you have a combustion chamber and you have a stroke, piston cylinder problem. And this guy in the very top, like this, in the car, inside the piston. This is the piston cylinder. And this guy creates a spark every stroke. In the very end, in the second stroke, get a spark. So we have a combustion. Without this spark, you cannot have this. So I used to tell this story. For the taxi drivers, they are kind of, like poor guys. What do you do? This guy, after a while, covered with some kind of exhaust materials. So after you burn, like for a month or two, and they are driving a lot, some of them are very good. They open the engine, they get this spark plug, clean it, and they can continue another month. So every month or two, they replace it. They said, no, how about I can just take it out, clean it, clean this, the head of the spark plug, so they can create a new spark, and they continue 2 more months. That's very good to save money for another 2 months. So this is a part in the engine. You can just take it out and clean it and put it back and fix it. It's called, we have 4 cylinders, 4 spark plugs. I don't know, do you have seen it, you guys? If you just search online about spark plug, you will see it. It's not expensive, but like I think $100. They are 4 of them. If you have 8 cylinder, which is very rare, you can see 8 spark plugs, 8 cylinders. Okay, guys, let's take an example. The spark plug, like gasoline engine, or Otto cycle, like we're gonna talk about it now. Otto cycle, Otto, O-T-T-O. Compression ignition is different, like diesel. It's actually, we compress the fuel and the air, the temperature goes very high. This temperature enough to create the ignition, which is kind of a spark. So we compress the fuel and the air until the temperature goes to certain temperature, they create ignition. So it's called compression ignition. So you did something, you compress them until certain temperature, this creates ignition. There are also in this chapter, we have 3 famous measurement of performance. So we have something called R, something called MEP, something called displacement volume. R is compression ratio. So for any engine, we have something called compression ratio is R, which is maximum volume over minimum volume. Like when we have a stroke, the maximum volume divided by the minimum volume is called R, compression ratio. Usually you use a symbol R small. MEP mean effective pressure, which is W net divided by Vmax minus Vmin. So if you have a cylinder, it creates for you some power, some work. This is power or work. Divided by the Vmax, it's actually work. Divided by mass, the volume creates pressure. This is mean effective pressure, MEP, something important. So when I ask you a question in the problem, I will not ask you for the power or the work. I will ask you MEP. I will not ask you for Vmax or Vmin. I will ask you compression ratio, or I give it to you input in the problem. Displacement volume is the sigma of Vmax minus Vmin. All the maximum volumes. So when you buy a car, for example, you say this car has, let's say, 3 liters, 3.3 liters. So you have the maximum volume 3. This is cc. So when you buy a car, you say 3,300 cc or 3.3 liters. It means the total volume, Vmax minus Vmin, for the 4-cylinder, 5, 6 cylinders, 8 cylinders. The total volume is 3,300 centimeter cube. The more you have, the better the engine is, the more power you can get, the higher speed you can go, the maximum what you can carry, for example, truck. So we wish to have this as maximum as possible per cylinder or all cylinders. So this is the maximum or the total difference between the maximum minus minimum volume. So you have 4 cylinders. Let's say you have 4 cylinders. Cylinder 1, cylinder 2, cylinder 3. This is the Vmax minus Vmin. Vmax, we're going to discuss this now. Vmax minus Vmin. The total of these 4 is called displacement volume. Let's take an example, which is Otto cycle. We're going to give example about everything. We're going to repeat everything in one cycle. How we can this assumption going, how about this applications or this performance measurements, which is in 9.5, Otto cycle. Like the car or the truck engine. Otto cycle 9.5. We used to say 4-stroke engine. We have 4 strokes. So we have this plot, the PV diagram. So there is something important here, guys. If you have PV diagram or TS diagram, in TV diagram we started in this area. TS diagram we started in this area. So we usually start in the bottom right corner, this area to start, and this area to start. All the problems, if you start here and here, you are kind of safe. The bottom right of PV diagram, the bottom left of the TS diagram. Let's see this one. We start the bottom right here. This is one. This is the first one. We have compression, isentropic compression. Isentropic, something like this. This is called isentropic compression. It means pressure increases and we have compression, volume decreases, and it's isentropic. This is constant isentropic line. Can this way or that way, but this is the constant entropy line until 2. So from 1 to 2 for an Otto cycle is constant. We're gonna describe this in details now. 1 to 2 is constant, or constant entropy is compression, isentropic compression. Then we have heat addition. Heat addition, we said it's constant volume. Like we go vertically, constant volume. This is heat addition. What happened? The volume is the same, and whoop, jump from here to 3. Then repeat the same thing. We got the work, expansion, then we have heat rejection, which is Q low. Let's plot this cycle. So 1 to 2, 2 to 3, 3 to 4. Let's plot what happened in reality. I'm gonna plot exactly what happened in reality and how this look like in reality. This is exactly what happened every time when you drive your car, when you ride a bus, when you ride a motorcycle. This is exactly what happened. What happened? We have a piston. Let me use the same vocabulary in the lecture. We have a piston. We have here 2 inputs. We have a spark plug. We have here 1 output. So here we have a valve for air and fuel. We have here a spark plug. Spark plug. And we have here exhaust valve. Exhaust valve. So this valve open when we dump the exhaust out. This was open when we want air and fuel go in. So initially, let's say everything is closed. Here, this is kind of filled with air. The piston is here. Let's say it's open, and this is a cylinder, and this is here, like this. It's filled with air. Here, we have big volume, V max. And this is V min, minimum volume. The piston was here, and this is closed, and this is closed. The cams are up. I will show you the video now. So I'm gonna go from 1 to 2, compression isentropic. So if this is a 2, the first stroke, so the first valve is closed, the spark plug is there is no fire, the second one is closed. So this piston was here, now it's here. This is called the V minimum. So this is state 1, this one. Volume is big, volume is huge, the pressure is low. Now the volume is so small, the pressure is high, I'm compressed, and everything is closed. Okay, guys, this is state 2. What happened? I will put here spark, ignition. Can you hear this, guys? Can you hear it?
Yes, we hear it.
It's not important, but just a stupid joke. Anyway, so what happened, guys? When you put this ignition, fire happened here. I added heat. So the volume is constant, the volume is the same. So the heat increase, jumps from 2 to 3. Jumps from 2 to 3. So 3 is the same thing, but with higher heat. It has huge heat, huge energy. Pressure larger, temperature larger, jumps from 2 to 3. I added heat. I make a start ignition. So this high pressure, high temperature will push the piston down. Actually, this piston is connected to the crank of the engine. This crank will start to, this arm will rotate, create a torque force, spin our shaft where the car moves. This huge pressure will push this down. So 3, I'm still here. But now I have pressure is huge, temperature is huge due to sparking. This spark, I have huge pressure and temperature here. Pressure is high, temperature is high. What happened? This piston will be pushed down. So it will be here now. Go back to the maximum volume. So now it goes to this point. This is 4. So actually from 4 to 1, there is another stroke. 4 to 1, what happened? I go up and down just to open this and go up. Let it go, then push down, let the air come in, then I start over. So 1, 2, 3, 4. Here in 4, this is called one stroke. Goes up, then it goes down. The piston goes up, then goes down. Here, it goes up and down. Then repeat again. Up, down, then up and down. Why up and down? This valve will open. Exhaust will open. When it open, when I go up, this one was closed. This is open now. So the exhaust will go. You will see the smoke going out from exhaust in the back of the car. We wish to be CO2 and H2O. We get all complete combustion. So when it goes up, everything goes out. Then this guy will be closed. This will be open. When it goes down, it will suck air and fuel. Then it go back here. This is called 1. Then this valve will close. Then repeat. Compression, spark, high energy, push it back. Up and down. This is called 4-stroke. 4-stroke. This is called 4-stroke, guys. Okay? Let's plot it. Let's draw it here. In reality, what happened in reality? 1 stroke, 2 stroke, 3 and 4. So this is called a stroke. This is 2 stroke. Then another 3 and 4. So in reality, this is what happened. Here, intake, close. Then we have ignition, compression. Then we have power. Then we have push it down. Exhaust valve open. Exhaust open. Then it goes like this. Fill with air, go back. This filling, filled with air. So here, go back like this. Intake close. Intake is closed. Intake open. So let's say you started here. Open, fill with air, close everything. Now, compression, ignition, power, exhaust, which is we go back here, then they go back. This is the real PV diagram, but we neglect this part. We neglect the open and shut down part. We neglect this part. So we have compression, isentropic compression, heat addition, power, exhaust or ejection. We assume this does not happen. This is happening in reality. So this is 1, 2, 3, 4 strokes. We add air, compress, burn, get power, exhaust. Add air, compression, burn, get power, exhaust. From this point to that point, exhaust was open. Exhaust valve was open. So just let every smoke go outside. We don't care about this part. We said we're gonna start here and everything is closed. Compression, isentropic compression. The first stroke look like 2-stroke assumptions. Isentropic, it's a little bit slanted with high slope, something like this. Isentropic compression. Then we heat addition at constant volume. Its reality was curved like this, but we assume constant volume. 1, 2, 3. Then we get power. This is what we get, the power. Then have 4. Now this is the rejection, which is actually exhaust, but we call it's called heat Q low. So this is Q high. This is Q low. Q high minus Q low is W net. The area under the curve is work net. Any questions? Any question, guys? So far, so good. We're going to repeat again with equations. Let's repeat everything again with equations. Equations will be like this. I'm going to move this part. Let's go one by one. 1 to 2. What is happening here, guys? Here is compression. Volume decreasing. we have isentropic. So 1 to 2 is isentropic compression. So delta S is 0. If this is air, you can use isentropic relationship. For example, T over T or P over P equal T over T to the K over K minus 1. P over P is V over V to the K, which is 1, 2, 1, 2. Here is 1, 2. Here is 2, 1 because it's inverse with volume. So this is called isentropic relationship. So if you have here between 1 and 2, it's isentropic. If you have P1, T1, and you just have here, for example, P2, you can get T2. Usually, we have V1 and we have V2, which is compression ratio. So you can get here easily T2. From where? Isentropic relation. This is unknown, but can be calculated from isentropic relation. So you can say, combine this and this, you can get T2. And because V and T are related. 2 to 3. 2 to 3 is what, guys? This is what? Heat addition at constant volume. Heat addition at constant volume. We can say Qn, per unit mass, CV, T3 minus T2. So let's say you get T2. Let's say you have V1 and V2 and T and V2. V1 and T1 and V2. You can, from isentropic relation, get T2. If you have T2 and T3, you can get Q. If you have Q, you can get T3. This is the heat addition at per unit mass. If you want heat total, multiplied by mass, air total. Like air and fuel, because we assume fuel is air. Just MCV delta T. That's exactly heat addition, constant, closed system, constant volume. This is closed system, guys. This is cylinder, and I'm compressing, or actually I'm still the same thing, but I'm adding heat. I'm adding heat at constant volume. So CV delta T. It was originally Q minus W equals delta U. But because because closed system, there is no work, so Q equals delta U, which is MCV delta T. Okay, guys? It was originally first law of thermodynamics for closed system. How about 3 to 4, guys? 3 to 4. Exactly same as 1 to 2. So isentropic, but expansion. So remember, V1 equal V4. V1 equal V4. If you have, for example, T3 and P3 or V3, actually, the volume here is the same. The volume here is the same. Between this point and this point, the same. Between this point and the same. So V2 equal V3. If you have V2, you have V3. If you have V1, you have V4. If you have T3 and V3, you can easily get T4. Why? The volume here and temperature, isentropic relation with the volume here, which is and temperature, you can get T4 because isentropic. So if you have, for example, 3 and 3, you can get, and of course, like let's say V4, you can get T4. Isentropic relation. How? You can say T4 over T3 equal V4 over V3 to the power K minus 1. Something like that. So you have T3 from the heat. You have V3, which is V2, V4, which is V1, power K minus 1. K is specific heat ratio. You can get T4. You can get T4. Why I want T4? Because 4 to 1 heat rejection at constant volume. Heat rejection at constant volume. Somebody tell me what is Q out or kilo here equal to what? What's Q out or Q low? Look what here. Small. Between 4 and 1. What is the Q, guys? Anyone? Same as Q high, but there. Constant volume, MBC delta T. Constant volume. So what's Q is?
CV T1 minus T4.
4 minus 1. If you want the Q absolute, yes, it's CV T4 minus T1. The bigger minus lower always. That's it. If you want the total, multiply by mass. I've seen a lot of question here. Oh, yeah, I did not post yet the lectures. What is this? Guys, are you talking? This is not a chat. Oh, yeah, it's a chat, yeah, but for me, not yourself, with your friends. Okay, you are biased and selfish without realizing it. This is for me or yourself? Talking to me? Anthony? Mean effective pressure, yes. So this chat, guys, if you have a question and somebody can answer it, is yeah, go ahead. But don't have kind of side discussion. So here we are describing what's going on in Otto cycle. Otto cycle, it's a 4-stroke cycle. We simplified it 2-stroke. Compression, heat addition, power stroke, then heat rejection. Compression stroke, heat addition, power stroke, heat rejection. It was originally heat rejection, go inside. We neglect the 2 strokes of exhaust and intake. We neglect them. If you go to the book, you will see this in the given details, but we care about compression isentropic, which means isentropic ratio between 1 and 2. If you have 3 information, you can get the force. So ideal gas law applied here, ideal gas law applied here, ideal gas law applied here, ideal gas law applied here. Between this and this, we can apply isentropic relation, only 1 and 2, only 3 and 4. Isentropic relation between 2 states, state 1 and state 2. This is called isentropic relation. But for a state, ideal gas law, PV equal RT. PV equal RT, PV equal RT, PV equal T. This is a state information, not a process. So for every state, PV equal RT, PV equal RT. That's correct. That's called ideal gas law. Isentropic, P over V equal T over T. We need this later in other cycle like Brighton. So keep those for Brighton cycle. We're talking about gases. But here we care about T and V. Actually, T and V, the most important thing. Because volume ratio is V2 over V1, V1 over V4, and so on. This is the compression ratio. 1 over 2 over 2 over 1. Actually, it's 1 over 2 because it's bigger volume minus lower volume over lower volume. Okay, guys? But once you have this compression ratio, you can get from just T1, V1, and V2, you can get T2. If you have T3, you can get everything. Why? V1, T1 and V1. And you have V2, which is V3, and V1, which is V4. So you have volume here, volume here, volume here, volume here. You have T1, you can get T2, isentropic. You have T3, you can get heat. You have T3 and V3, you have V4, you can get T4. T4 and T1, you can get heat. Heat minus heat, get work. Q high minus Q low. Second law, or the pentagram. That's it. So the whole cycle solved by V1, V2, which is compression ratio, which is V3 and V4. T1 and T3, you have everything. T1 and V1, you get V2, T2. T3 and V3, you can get T4. T3 minus T2, you can get heat here, multiplied by CV. T4 minus T1 you can get here, which multiply by CV. Q minus Q equal W. So we combine together everything we learn. First law of thermodynamics, closed system. First law of thermodynamics, closed system. The second law or first law of thermodynamics for the whole cycle. Work Q high minus Q low. Is it easy, guys, or hard? Is it easy or hard? So let's drive something. Guys, it's hard. Okay, it's easy. Let's say easy. Is it easy, guys? No one replied. It's hard. Guys, somebody reply, please. Is it hard?
It's good.
So please try to focus as much as you can, as best as you can. So eta thermal here is what? Let's talk about eta thermal Otto cycle. So eta thermal Otto. It's 1 minus Q low over Q high. 1 minus Q low over Q high. Q low is here. CV delta T is 1 minus CV T4 minus T1. Here, Q high was Qn, CV delta T, CV T minus T. So air is the same air. Assume air, everything is air. So 1 minus T4 over, let's say, T2 minus T1 over T2. Let's do it exactly compression ratio. Compression ratio, you need to have. So we have originally T1 over T2 equal V2 over V1 to the power K minus 1 and equals to T4 over T3. 1 and 2 compression ratio or 1 over compression ratio to the K minus 1. 4 and 1 is 1 over compression ratio to the K minus 1. This is compression ratio, by the way. This is 1 over R. V1 over V2 is R. V2 over V1 is 1 over R. So this and this isentropic. This and this isentropic. So this is the ratios. So let's divide by what? T4. I want T3. T1. I think we divide by T1. Let's divide by T1. So if we divide by T1, divide by T1, T1 over T1, T1, T1. You will finally, I think if you manipulate, it will be 1 over R to the K minus 1. K minus 1. Yes, correct. RC, we usually RC. If you want RC, compression ratio RC or R, because this is compression. RC K minus 1. This is just if you want to get the thermal efficiency. If I told you compression ratio was like, let's say 7, it's a number. If you have K 1.4, you can get exactly the thermal efficiency, let's say 35%. If you have compression ratio and K is 1.4, you can get exactly what the thermal efficiency. So let's together watch a video about this. Okay, guys? You want to watch a video?
I love videos.
One second, guys, 1 second.
In that fraction you just wrote down in the top right corner, does it say r subscript c to the k minus 1?
What do you say?
For the fraction you wrote in the top right corner, does that say r subscript c to the k minus 1?
Exactly.
All right, thanks.
Okay, let's watch this video together. And okay, ignore all the movies and stuff like that. Okay. Can you see, guys?
Yep.
Can you hear it?
Yep.
Otto engine is a combustion engine and is considered to be a technological milestone of human thought. It was named after its inventor, Nicholas August Otto. Otto engines are used in motorcycles, cars, and other vehicles. This animation explains the Otto engine as a four-stroke engine. This engine is composed of a piston that moves up and down in a cylinder. The highest point the piston can reach is called top dead center. The lowest point it can reach is called bottom dead center. The volume between both points is called engine displacement. The piston is connected to the crankshaft through the connecting rod. The crankshaft transmits the rotational movement to the gearbox and consequently drives the wheels of a car or motorcycle. Shafts are installed on top of the cylinder, which control the intake and exhaust valve. The camshaft is connected to the crankshaft through a belt. More often than not, the crankshaft to camshaft gear ratio is 2:1, which means that for every 2 revolutions of the crankshaft, the camshaft will rotate only once. An Otto engine has a spark plug that uses an electric spark to ignite the fuel charge. The four-stroke Otto engine is an internal combustion engine in which the piston completes 4 separate strokes. The first stroke is called intake stroke. Here, the intake valve is opened by the rotating cam. The air-fuel mixture is sucked into the cylinder. The second stroke is the compression stroke. The intake valve is closed and the air-fuel mixture is compressed to a high degree by the piston. The higher the compression ratio, the more mechanical energy the engine can squeeze from the air-fuel mixture. Higher compression ratios, however, make self-ignition more likely. The third stroke has been named power stroke because this is the process where power is produced. The air-fuel mixture explodes. The force created by the explosion causes the piston to move down. The fourth stroke is called exhaust stroke. In this stage, gases remaining in the cylinder are removed from the cylinder through an exhaust valve. The crankshaft transmits the rotational movement to the gearbox, and the driver can drive. Often, engines of today feature more than one cylinder to power cars or motorcycles in order to increase speed and smoothness.
Okay, guys, I wish that you enjoyed this video. Did you?
Yeah, pretty cool.
So this is exactly what happened every time. One second. Yes. Every time you drive, actually there are tons of videos for every cycle. If you like it, go ahead and watch thousands of videos about how every stroke look like. You can, some of them you can follow these lines and see the power output or the results. Maybe you're not gonna see equations, but you're gonna see what happened exactly in this.